All right. Good morning, everyone. Those of you who are here and those of you who are not here in person. So we are starting module 5 today. I'm going to call these primal-dual algorithms. So have any of you seen any primal-dual algorithms before?
Come across them in support vector machine learning.
Okay, in machine learning. Okay. Approximation. Okay. I see. Right. Okay. Anyone else who has seen it? Anyone else who took approximation? You took it as well? Okay. All right, so there will be probably some degree of repetition, but hopefully the approach will be different, the approach of covering material at least. All right, so I want to start with shortest paths. Right, so let's just remind ourselves of the setup of
You
the
need to
problem.
share the screen.
Oh, I haven't shared the screen. Thank you. All right. Okay, now can you see the screen?
Yes.
Okay. Great. Thanks. All right, so we'll start with shortest paths. That will be our first combinatorial optimization algorithm using the primal-dual method. And then eventually we will move on to more complicated algorithms like matchings, minimum cost perfect matchings. Right. So let's just remind ourselves of the shortest path problem. So what's the input? We are given a graph as usual, and we have two distinct vertices, S and T.
Sorry to interrupt. Some students were not able to find MSB 360. So
Okay.
can anyone in the any of the participants guide them? They are asking in the WhatsApp group.
Okay. Yes, I shared the location of MSB. So maybe it's on the second floor.
Entrance and then we found stairs, right upstairs.
I don't know. So can someone?
Yeah, so maybe one of the students will reply
One
on
of
the
the
WhatsApp
students.
group. Yeah, if you can just send the direction on the WhatsApp group how to get here. Yeah. Right. Thanks, Shantini. Okay, and we have a cost function that assigns each edge a non-negative real number. Okay, and our goal is to find a shortest path let's call it a Q, and in particular shortest here means one of minimum cost, right? So the C can be thought of as a cost function. Okay, it's also standard to call it a distance function, and then it will be the path of minimum distance, doesn't matter. All right, so this is the problem we want to solve, but we want to use LP duality theory, right? So let's write down the IP for this problem, right? We have done this in the module 1. So the integer linear program is as follows, right? We are trying to minimize the cost of the path. So that can be thought of as C transpose X, where X is going to be our vector of variables that indicates whether an edge is in the path or it is not in the path, right? So let me just say we are thinking of X as being 0, 1 vector, right? And we are subjecting it to the following constraints. So does anyone recall the constraints that we wrote for the shortest ST path problem? So how do we ensure that the selected set of edges is a ST path? S is here, T is here. How do we make sure that the set of edges we have selected is going to be an ST path, or it's at least going to contain an ST path?
M alternative. M alternative.
No, you're thinking about matchings. I'll give you a hint. It's related to cuts.
It meets some cut. It meets every cut.
Meets every cut, right? So you want the set of edges selected to meet every ST cut. If there's a single ST cut that it doesn't meet, then it can't contain an ST path, right? Okay, so that's our constraint. So for every ST cut, we have a constraint. So I'm going to write it as A transpose X, at least one. And here the matrix A has rows indexed by the ST cuts, and the columns are indexed by the edges of the graph, right? So what it's saying is, sorry, I did not mean to write a transpose. I am sorry. I meant to write AX at least one. Okay. So it's saying that for every ST cut, you look at the edges selected and at least one edge has to be selected. Right? And we also want our vector to be non-negative. I said 0, 1 vector, but actually when we wrote the ILP, we allowed it to be any integral vector. Okay, so X is, we are thinking of X here as an integral vector, which I'm just going to put in the constraints, right? So X is integral. Right, so what this will do is, if you take any feasible solution, you will have a set of edges. Some edges, notice that because it is integral, you could assign the label 3 to it rather than 1. But if you're trying to minimize the cost, then you will choose necessarily 0 and 1. The only exception is when you have an edge whose cost is 0. But if you're, in particular, if all edges have cost positive, then the optimal solutions will be 0, 1 solutions. There is no reason to choose an edge thrice, right? So that's just a technical point. So this is what we are referring to as the ILP for the shortest ST path problem, right? So let's call this P prime. Okay. And we also know what is an LP relaxation. So we are going to throw away the integrality constraints and write down the LP relaxation. Right? So now we are switching from the integer world to the fractional world in some sense, right? So the LP relaxation is the same thing right? Any questions or concerns at this point? And everybody has seen enough of this stuff in assignment 1 and module 1, I suppose. Okay. All right, but now we have duality theory. So let's write down the dual of this, because that is what we are going to use to devise our algorithm, right? So the dual of this problem is the maximization problem, B transpose Y. So that is 1 transpose Y, right? Because the right hand side here is the one vector, all ones vector, subject to the following constraints. So we have got A transpose Y, C, and what about the Y variables? Can anyone tell me what do I put in these question marks? Less than equal to for the first one. Okay. Greater than equal to 0 for the second one. Okay, thank you. Right. So Y's are non-negative variables that satisfy these constraints. So let's try to understand what these constraints really mean combinatorially. So this is just a bunch of equations. Let's try to understand what each inequality is really telling us. Right. Okay, so I'm going to call it interpretation of the dual. If you like, you can call it a combinatorial or graph theoretical interpretation. So what's going on in the dual? We have a variable for each cut. For each ST cut, we have a variable, right? And okay, so let's just write that down. So maybe I'll introduce some notation which was used on your assignment 1. So let's say script F is the collection of all ST cuts, right? So the dual has one variable for each ST cut. So a variable yf for each f in script F. Okay. And what is this constraint telling us? So I want to think about, right, this is in the matrix vector notation. I want to think about what any particular row of this constraint is telling us. Right, so how many constraints do we have in this? For each edge, there is a constraint, that's right. Okay, and what does each constraint tell us? What is less than? What is the thing on the left hand side? Is this a number of cuts or is it, let me call these labels. Let me call these variables labels. Right, so there is a label for each ST cut, which is the dual variable. And what is the left hand side? It is the it is A transpose multiplied by Y. So if you think about any row, right, the Y's are labels.
Sum of the labels of the
Right, it is a sum of the labels that of those cuts that contain this edge, right? So each row is corresponding to one edge, and what the matrix is telling you, right, if you think about the incidence matrix, which here has rows indexed by edges and columns indexed by ST cuts because we took the transpose, right? What it's telling you is that for any edge, if you sum up the labels of the cuts that contain that edge, the sum should be less than equal to the cost of that edge, right? So
this was the last question on the assignment.
yes, yep. So the summation of, so look at all the cuts that contain this particular edge for any edge of the graph, and let's sum up the labels corresponding to these cuts, and that should be at most the cost of that edge, right? All right. And what else? The labels are non-negative. So all the YFs are non-negative. Right? So that is what our dual is doing. It is trying to maximize the sum of the labels, where the labels are assigned to each ST cut. And we want to make sure that the labels are non-negative, and that for every edge, the sum of the labels that contain that edge, the sum of the labels of the cuts that contain that edge, is at most the cost of that edge. Right? That is exactly what the dual is. All right. Great. So now let's go to your assignment 1, problem 5. I call them exercises because otherwise it confuses with the word problem. So it is about the shortest path problem, right? So what did you prove in that? You proved that, so let's look at part A. Right, so we are not going to prove using counting, which is what you did on the assignment. We are going to prove the same thing using LP duality. So if Q is any ST path and Y bar is any dual feasible solution, which is your set of labels, right? So there I use the notation L for each cut. I gave it a label L of that cut, right? but what they really are is they are dual feasible solutions, right? Then what you proved is the following: sum of all the labels is less than equal to the cost of your path. I changed some notation. I think I use P for the path, but now we are using P for the primal linear program. Okay, and that is nothing but summation of the cost of all edges in the path. Right? So this is exactly what you proved in that particular part in assignment 1. Right? All right. So now I want to prove this using weak duality. Can anyone tell me how to proceed? So we are given an ST path and we are given a dual feasible solution, right? So how can we make sure that we are somehow able to apply weak duality over here, right?
Already here the C transpose X should be less than 1 transpose Y. So 1 transpose Y is the summation of all the Y variables.
Okay.
C transpose X, because X is the
So what is X?
X
So
is
maybe
0,
someone can
1.
tell me what X is.
0, 1. It's binary.
Okay, so how do I get it from Q?
If it is in Q, it is 1, otherwise it is.
Right, exactly. Right, so we are going to construct a primal feasible solution based on the path given to us, and then on that primal feasible solution we are going to apply weak duality, right? So let X bar be the primal feasible solution corresponding to the path Q, right? So if an edge is in the path, you give a 1 to it, otherwise you give a 0 to it, right? All right, that has to be a primal feasible solution based on how we wrote the primal, right? So every ST path corresponds to a feasible solution of the primal, right? In particular, it is a feasible solution for the IP, but then of course it is a feasible solution for IP, so it is also feasible for the LP, because you have just thrown away some constraints, right? The integrality constraints, right? Okay, so by weak duality, we know that the value of X bar in the primal is less than equal to, let me think about this. No, the primal is a minimization problem, so it is greater than equal to. Okay, let me just write value of Y bar in the dual. Value of Y bar in the dual, which is our maximization problem, is less than equal to the value of X bar in the primal, which is our minimization problem, right? And what does that say? That means that 1 transpose Y bar is less than equal to C transpose X bar. But 1 transpose Y bar is nothing but the sum of all the Y labels, right? So that means that the summation of all the labels is less than equal to C transpose X bar, which is nothing but the summation of all the edges in the path by the way we defined X bar. And that is exactly the cost of our path. Sorry, Q. My bad. All right. So that proves assignment 1, exercise 5, part A, using weak duality. Okay. Are there any questions or concerns at this point? Anyone in the WebEx call? All right. Okay, so now, so we are going to use weak duality for our algorithm, and we are also going to use complementary slackness, right? So let's move towards complementary slackness. Let's try to think about what the complementary slackness conditions tell us in this particular case. Let me copy paste the primal and the dual. Sorry. Okay, so I think I just have to okay. Okay, good, not bad. Okay, maybe I see I don't have too much space here. Let me just write down the certain parts again. Okay, so we are maximizing 1 transpose y subject to A transpose y at most C and y being non-negative. All right, so let's write down the complementary slackness theorem actually for this particular pair of primal dual LPs. So let's say X bar is a feasible solution to the primal and Y bar is feasible to the dual. So we are going to say, well, the theorem says that X bar and Y bar are both optimal solutions for the primal and for the dual respectively, if and only if they satisfy the complementary slackness conditions. Right, so I want to write down the CS conditions next. So maybe I'll just say CS1 and CS2. Okay. All right. So let's think about the first one, right? So we look at a primal constraint. Either the primal constraint is tight or the corresponding dual variable is 0, right? So can someone tell me, looking at these two, what it looks like? What is it really saying? Right, so the primal constraint, there is one constraint per ST cut. So I'm going to write for each F in script F, either something happens or something else happens.
Is non-negative, it is only once. Statement should be like, if the edges belong is like, if the edge meets more than one cut, then it has to have 0.
Yeah, we'll come to that. But first, I just want to write down a very direct interpretation. We will come to, so right now, notice that we just have an X bar and Y bar, right? We don't have a path. We will apply it to a path later. But right now, you just have some primal feasible solution, right? It doesn't have to be a path. It will contain a path. That is something we proved in module 1. Every primal feasible solution, if you look at the edges that are, well, if it is an integral solution, then yeah. So right now we could just even have a fractional solution, right?
I think the interpretation one edge in any cuts in like yi is 0.
Okay. I just want to write down the most basic interpretation. So on the left, if you look at the constraint, right, it's a summation of something. It's a summation of some x bars. Either that is equal to 1. So what is it a summation of? We are not trying to go to a combinatorial interpretation right now, because we could have a fractional solution, right? So we will get to the combinatorial interpretation, but right now we want to do something that applies to any solution.
Sigma AI XI labels edges in the cut.
Is it labels of edges, or are we looking at the labels are y's?
Presents labels the XE, not Y's.
Okay. Okay, sure. So the labels, so the x values corresponding to the edges in the cut equals 1.
Not equals to more than.
Okay, so I'm thinking of either the constraint is tight or the dual variable is 0, right? Just writing down in the very standard way, right? So if you look at all the edges that belong to this cut, right, then there's sum of the x bar values is exactly equal to 1, or y bar f is 0, right? That's all it is. Okay, so we'll come to the combinatorial interpretation a bit, right? And what about the second CS condition?
Labels and its
Okay,
if it's equal to cost of edge or the XE equal.
right. So if you look at any edge, right? So if you look at any edge of the graph, and you look at all the labels containing that edge, labels of the cuts containing that edge, right? So take all the cuts containing that particular edge, and you sum up their y bars. Either that is exactly equal to the cost of the edge, or the edge variable is 0. Right. All right. So let me just see how much more time we have. Okay. All right. Any questions or concerns? Everybody happy with the CS conditions? Yeah. All right. So I'm just going to copy down the CS conditions. Oh, okay. Let's see. No, this is not what okay. Okay. And let's move on to page 3. Let's paste this here. Okay. So these are our CS conditions. And now I want to apply it to a path, right? So now what we are going to do is we are going to take a specific ST path, Q, and a dual feasible solution, y bar. So the dual feasible solution, we are going to allow it to be fractional, right? What we really want is an integral solution to the primal LP. We don't care about the dual solution. It could be fractions, whatever, right? So we'll take any ST path and a dual feasible solution and try to see what these constraints, what these conditions tell us, right? So let's see. Let's call this a combinatorial interpretation. And this is related to your exercise 5 in assignment 1, part B. Okay, so now let's suppose Q is an ST path, right? So we are in our usual setting. G is a graph. I mean, all of the setting applies. So we have an ST path and we have a dual feasible solution. These are your labels in that exercise. Okay, so now let's try to understand what these conditions are telling us. Let me actually just call them 1 and 2 now, so that I don't always have to write CS1, CS2. Okay. So the way I want to think about this is if y bar f is not 0, right? So then it has to be greater than 0, right? Because the y bars are non-negative variables. So if my y bar f is greater than 0, right? Then what does the left-hand side tell us? So if the y bar f is equal to 0 is not true, then we know that the other thing must be true. So now how do we interpret this combinatorially? Meets only one time, right? Exactly. So the intersection of f and q is exactly 1. This is for each f in script f. Right? So whenever a particular cut has been assigned a non-negative, a positive label, we want to make sure that exactly one edge from this cut is used in our path. Right? All right. And now let's look at the second one in the same spirit. Okay. So let's assume that x bar e is not 0. Well, but if it is not 0, what must it be? Then it has to be 1, right? It is in the path. Basically, it not equal to 0 b is the same as saying that it belongs to the path q, right? I'm thinking of the path as a set of edges. Okay, so I'm not going to write e of q. I'm thinking of the path itself as a set of edges, right? That should be enough to define a path. So either if the edge is in the path, then we know that this must hold, right? So the sum of the labels of the cuts containing that edge must be exactly equal to the cost of that edge. So this is exactly what we wrote down. Right? And this is for every edge of the graph. So what does this mean? If we can find a path, if we can find an ST path Q and a dual feasible solution Y bar such that they satisfy these two conditions, then what can you say? Then the path is the shortest ST path, right? It is actually a optimal solution to the primal, but if it is optimal solution to the primal and it is integral, in particular it is 0, 1, right? Well, then it also has to be an optimal solution to the P prime, our IP. Right? That is exactly the plan for our algorithm, right? So the observation here is that if we can find a path Q and a dual feasible solution, Y bar, such that Q and Y bar satisfy conditions 1 and 2, then for sure Q is, so I mean here an ST path, find an ST path, then for sure Q is the shortest ST path. Right? And this is going to be the driving idea behind our algorithm, right? So what we want to do is somehow ensure that our algorithm satisfies these two conditions. Whatever the algorithm outputs at the end satisfies these two conditions, right? And in fact, these two conditions will also drive the design of our algorithm. They will actually guide us in discovering the algorithm. That's the main essence here. So these are the sort of guiding principles behind the algorithm. All right. Are there any questions or concerns at this point? No? All good? Okay, so let's begin. We might not see the whole algorithm today. In fact, we definitely will not. We have just 10 more minutes to go. But in fact, I don't want to show you the whole algorithm in the first go. I want to focus on one of these two conditions and eventually worry about the next condition, right? So let's start with the second condition.
So here we are saying that we should be, if we find the q and y, but how do we even like know that? How do we even find the y?
Right, we are going to start exactly there. Yes. Yeah, that is exactly the point we will start our next discussion at. So I believe we go to one more page. Okay, this is page 4. All right. So if the edge is in the, I think I made a mistake in copying. So if the edge is in the path, right, that is what we want. All right.
So will we be iterating through all the cuts in the graph?
No, we won't. Yeah. It might seem at first that we have to, but there are ways to avoid those kinds of things. So it is actually going to be a polynomial time algorithm. I don't know if we'll focus so much on the running time. I want to focus more on the correctness, right? But you can actually go through it and see that it's not an exponential time. It's everything can be done in poly time. Right? Okay. So let's begin our algorithm with thinking about this particular condition. So for now, let us focus on the second condition. Okay, we'll then worry about how to get the first condition to work. Okay, so the first question is, of course, what Varun raised. How do you even find a dual feasible solution? Right, so let's think about that. So can anyone see a dual feasible solution? Right, all zeros. Exactly. Yeah, good. So the answer is indeed yes, it is the all zeros vector. So let's write down the dual. Maybe so we have the dual is our maximization problem, 1 transpose y, subject to 1 transpose sorry, A transpose, yeah. A transpose y is at most C, right? And y's are non-negative. Is that correct? Okay. So if you look at these constraints, it becomes clear that if you just set everything to be 0, you're done. Why are we done? Why does everything 0 work? What is one of the key reasons?
Cost is greater than
The costs are all non-negative. All the edge costs are non-negative, therefore it works. Right? So since the cost vector is non-negative, Okay, so that is going to be exactly our starting dual feasible solution. At each step in the algorithm, we are going to have a dual feasible solution, right? So in fact, one of the key points about the algorithm is that at each step of our algorithm,
So it's like the loop invariant.
we want to improve it. That is, at each step we will improve it.
But at every stage, it will satisfy that condition.
It will satisfy, yeah, it will be dual feasible, yes. So in that sense, yeah, that could be the loop invariant, yes, yes. It will be feasible, so that would be our loop invariant. So at each step of the algorithm, we will have a current, if I may call it, a current dual feasible solution, y bar, right? And the first one will be 0. This is the starting dual feasible solution. Okay. And we want to try to improve our dual feasible solution, right? Okay. So now I'm going to switch to an example and just see how we do this, right? And we are, as I said, we are going to focus just on condition 2. So we have another 6 minutes. So whatever we will see will not actually be the main algorithm, because we still also have to worry about condition 1. We'll come to that later, right? I feel that going step by step will make it easier as to why each of the each of the features of the algorithm, why are they there. So the general scheme is based on condition 2, but then there is going to be an additional step or an additional sort of pruning to get condition 1 to work, right? So there, or yeah. Anyways, it will become clear as we go on. So let's see. Do I want to continue on this page or do I want to start a new page? All right, let me think about this. Okay. So let me use 2 pages at a time. I'll keep switching between these 2 pages.
Can you change the view such that there are 2 pages set?
Is that possible? Maybe it's possible.
There is the view option.
View. Let's see, 2 pages. Oh, great. It is too small. Okay. Go back to view. Not 2 pages. Whole page. Okay, fine. Anyways, I'll try to meddle with it later. The problem is I have to come to this room to understand more how this works. All right. Okay, so let's get started. Let's draw one graph, which I'm going to use as our example for the entire algorithm. Maybe I should draw it a bit bigger. Okay, so let's say these are our vertices S and T, and let's call these U, V, and W. And let's put the costs on the edges. 6, 1, 5, 2, 4, 1, 2, 1. Okay. All right. So this is our graph G, and the cost function is what's given in the black color. We will have to use some other numbers. I'll use different colors for them to indicate what they mean. Okay. All right. So we just have another 2 minutes to go. Let me not. I'll just do one step for now of this incorrect algorithm, because we still need to worry about condition 1, right? But we're just focusing on condition 2 right now. Okay, so the current dual feasible solution is all zeros, right? So in fact, let me write it down as follows. So for each cut, so for each ST cut F, the corresponding dual variable is 0.
Is there a way to count how many ST cuts?
Yes, let's think about this. Do we see a way to count the number of ST cuts? So if you think of a cut as a set of edges, which is what it is, then it's a bit tricky, but you should think of it as arising from a partition of the vertex set. Right? An ST cut arises is a set of edges that arises from a partition of the vertex set. Right. Exactly. Right. So if you think about it that way, it's easier. The good news here is we are setting everything to 0. You don't need to keep track of what is 0. You just need to keep track of those cuts whose y variables have been set to greater than 0. Right? If you know those, then you know that the others are 0. Okay, so that's some good news. Right? So you don't need to go and set all of them to 0. Okay. That is partly answering the question he had asked. Do we have to keep track of all ST cuts because there's an exponential number of them? No. Okay. All right. Okay, so what is the plan now? So we want to figure out a way to get a better dual feasible solution, right? And we want to make sure that the second condition is always satisfied, right? What was the second condition? Let's see again. So if an edge is in the path, then that edge, the label's sum should be exactly equal to the cost of the edge. Okay, so let's introduce some terminology and we'll continue from that point tomorrow. So for any edge E, we will define the slack of that edge. Okay, so the slack of the edge E will be exactly the cost of the edge. So it is the right hand side here minus the left hand side, the labels of all the cuts that contain that edge, right? The sum. So minus the summation of all the cuts that contain this particular edge. Okay. And we know that this has to be greater than equal to 0. Right? That was our inequality from the dual, right? Yeah, exactly what you see here. Okay? So this is always going to be greater than equal to 0, and we will say that an edge is tight if the slack is 0. Right? An edge is tight at any step of the algorithm. An edge E is tight at any step of the algorithm if the slack of the edge is exactly equal to 0. Okay, otherwise we will say that it is not tight. Right, so whether an edge is tight or not depends on the step of the algorithm you are in. Right, it's a dynamically changing thing. Okay, and given a dual feasible solution, we will consider the tight graph, which will be the graph formed by only the edges which are tight. Right, because remember, our path has to be only from those edges that are tight. Notice that if an edge is in the path, then the corresponding edge has to be tight. Right, so at any step of the algorithm, the tight graph H is the subgraph formed by only the tight edges with respect to the current dual feasible solution. Okay. Right. So the idea is we want to find our path in this tight graph, right? If we find our path in the tight graph, and finally, let's say we have an ST path which is in the tight graph with respect to the dual feasible solution at the last step, then condition 2 is satisfied. So that is what we are going to do. There will be one problem we will run into. We will also need to satisfy condition 1. For that, we will use another trick. Okay. All right. So we might take about another 1 or 2 lectures to complete this algorithm in full detail. All right. Okay. So that's all for today. And we will continue with this example tomorrow, how to get to the next dual feasible solution. And we will compute the tight graph at each step and see how that works. Okay. All right. Thank you. I'm going to stop recording. Let me see if anybody's in the meeting yet. Okay, so it's just Shantini. So I'll stop recording.